Alright, what we have been given in example 1 is the zeros. So we know that this is what each of the x values are. -3, 1/2, and 1. So if those are the zeros, then we know the factors are x plus 3, x minus 1/2, and x minus 1, because you just flip the signs. So all we need to do is multiply these together. We just need to take 2 at a time, so we can pick whichever 2 we want first. Let's go ahead and pick the ones without the fractions first. So we'll go ahead and FOIL x plus 3 times x minus 1. So when we do that, we get x squared minus x plus 3x minus 3. When we combine like terms, we get x squared plus 2x minus 3. Now, since we already used the first one and the third one, all we need to do is take our answer and multiply the whole thing by the one that we haven't used yet, by the x minus 1/2. So I will go ahead and make a 2x3 box for that, because I like using the box for things bigger than 2x2. I'll put the x and -1/2 on the side, and I'll even make the 1/2 into a decimal. And I'll put the x squared, the 2x, and the minus 3 from that previous answer on the top. So I'll go through and I'll do the box method. We'll get x to the third, 2x squared, and -3x in the top row. -0.5 times x squared, that's -0.5x squared. -0.5 times 2 is -1x, or -x, and last -0.5 times -3 is +1.5. So let's just combine like terms and we'll be done. We have x to the third first. There aren't any other x to the thirds. On that diagonal we can combine 2 minus 0.5. That will leave us with 1.5 x squareds. We can combine these x's. -3 minus 1 is -4, and last is the plus 1.5, and we're done. You can always choose to multiply the factors in any order you want. So the zeros in example B are -2, 2, and 4, which means the factors would be +2, x minus 2, and x minus 4. My advice to you is to multiply this one and this one together first. When you do that, you'll see that you get x squared minus 2x plus 2x minus 4. The reason that's good is because these middle terms, -2 plus 2, cross out. So that answers x squared minus 4. So since we already used the first and second one, we just take this answer and multiply it by that third one that we didn't use yet. So when you do that, your answer becomes x to the third minus 4x squared minus 4x plus 16. There aren't any like terms to combine, so that's your final answer for B. The fundamental theorem of algebra is kind of a big deal. It sounds fancy, but we've pretty much already been using it with all the factoring we've been doing. Formally from the book says, every polynomial function with degree greater than or equal to 1, so we're not going to have something with a degree 0, because that'd be a plain number, and we're not going to have a negative degree, because we don't do that. Anything with degree greater than or equal to 1 has at least one 0, and the 0 might be a complex number, a plus or minus bi. That's what the book says. But I have a simpler way of telling you what the fundamental theorem of algebra is. I say that the degree, the highest exponent, tells you exactly how many zeros you have, including imaginary zeros, which we haven't dealt with up until now. We've had all real zeros, but they could be imaginary, and you might also have multiplicities. The point is, they all need to add up to whatever your highest degree is. So take a second and see if you can find an easier way to explain it than what I said. Basically, if your degree is 7, you need to have 7 zeros, whether they're imaginary or real or whatever. All right, so real quick, let's do this problem. We wouldn't be able to do this by factoring out a GCF because all 5 of those terms don't have a GCF. We can't split it in half, so what we're going to do is plug that into the calculator, type it into y equals, and hit second graph to look at the table so we can figure out where we have some real zeros. So if we do that, you'll see in the table that next to 0 in the y column, we have -2 and then 1. So that means for sure there's a real 0 at -2 and 1. We're going to use that information to narrow down the rest of the zeros by synthetic substitution. So in class I used x equals 1 first. So I'll put 1 in the box, and then we'll take the coefficients from the equation, 1, 1, 2, 4, and -8. It's standard form with no skips, so we're good. We'll do synthetic substitution, drop the 1. 1 times 1 is 1, 1 plus 1 is 2, 1 times 2 is 2, 2 plus 2 is 4, 1 times 4 is 4, 4 plus 4 is 8, and 1 times 8 is 8, and we get a remainder of 0. So that would be the next polynomial. Instead of x to the 4th, it'd be 1x to the 3rd, 2x squared, plus 4x plus 8. We could at this point try to factor that, but since we know another 0, we're going to do synthetic substitution again with the other 0. So we'll put -2 in the box, and we'll take those coefficients, 1, 2, 4, and 8, and we'll drop the 1. -2 times 1 is -2, 2 minus 2 is 0, -2 times 0 is 0, 4 plus 0 is 4, and -2 times 4 is -8, and 8 minus 8 is 0. So that leaves us with the next polynomial, 1x squared plus 0x plus 4. Could we factor that? X squared plus 4 equals 0? Well, we can't break it into 2 sets of parentheses, but we can solve it for x by subtracting 4 from both sides. We'll get x squared equals -4, and when we square root both sides, we get x equals plus or minus 2i. So we have 2 zeros right there, those are imaginary, and then we have the 2 zeros from up above. X equals -2, that's a real one, and x equals 1, that's also real. Alright, let's start factoring this last one. We can break this one up into 2 sets of factors by writing x squared and x squared. The factors of 16 that subtract to 0 are plus 4 and -4. So when we look at x squared plus 4, we can't break that up into parentheses anymore, but we can solve that by setting it equal to 0. So it'll be just like the one we just did. We'll subtract 4 from both sides and get x squared equals -4. And when we square root, we get plus or minus 2i. It's imaginary. We can factor the other side. When we do that, this one can be broken into x plus 2 and x minus 2. So when we solve each of those, we get -2, and +2. So there we have our 4 answers. 2 of them are imaginary, and then 2 of them are real, and that matches up with the degree. So we've used the fundamental theorem of algebra, and it all works out.